Hello guys, today in this short video we're going to talk about bending moment. And bending moment, we can imagine this type of thing in bending moment, like let ABCD be that longitudinal section of a beam bent under the action of equal and opposite couple tau at its end, and let n dash be its neutral axis, which we denote here. And consider the beam to be divided into two parts by a transverse plane through PS. Okay, so by P and S, it will be divided into transverse axis, and that will be KL. Okay, this will be due to the bending filament of beam above the neutral surface are lengthened. uh, you can see, which is this is the part peaking over KL. This is getting lengthened. Okay, this get lengthened and are therefore in tension. Okay, so they're proportional to left of PS exert a pulling force on the portion of the right of PS. Okay, the filament of the beam below the neutral axis are shortened, and hence their portion to the left of PS exert a pushing force. Okay, left of PS exerts a pushing force on the portion to the right. The resulting of this pulling and pushing force is restoring couple which balance the external couple responsible for bending a beam. The magnitude of this restoring couple is called the bending moment. Okay, and thus the bending moment, which may be defined as the total moment of all couples arising. Its bending moment is couple. Okay, you know that moment is couple. Defines the total moment of all couple arising from a bent beam and trying to resist its deformation caused by an external couple. Okay, so if we want to derive this, we will let us now consider a small part of beam bounded by two transverse sections PH and QR. Uh, PH and QR. Okay, so now let R be the radius of curvature of the neutral axis n dash, and let it subtend an angle phi and it is center of curvature O, and consider then a filament KL at its distance KN is equals to Z from the neutral axis, so that KO is equals to R plus Z. It follows that phi is equals to KL by Q, that is equals to angle is equals to arc upon radius, which I show you earlier, like. And now what we see is phi is KL, which is arc upon radius KO. Okay, radius is KO, or we can say less so, but I will say now KO. Okay, and we already said that KO is R plus Z. Okay, now I hope you get like n and s is curved, so from n to O, that is radius of curvature. That is radius of curvature, and radius of curvature and radius here are different. Okay, so we imagine radius of curvature will be capital R, and K and N, the distance of K and N is Z. Okay, we let that thing, so K is equal to R plus Z, and we can say pi is equal to KL upon KO, or KO means R plus Z. So writing it mathematically, we can say Q is R plus Z, and KL will be equal to R plus Z phi, and similarly N and dash will be equal to R phi. Okay, uh, uh, from the same thing, okay, you can just figure N and dash will be equal to R phi, and means the extension in the filament will be equal to KL is equal to R plus extension. Okay, this will be the extension is equal to R plus Z phi minus R phi. When you subtract this upon this, we will get the extension, and that is equal to Z phi. Okay, and longitudinal strain will be given by increasing length of original length, and that will be equal to Z phi by original length is R phi, and that will be equal to Z upon R. Okay, and thus the strain in the filament is directly proportional to its distance from a neutral axis. Okay, if y is Young modulus of elasticity of beam, then y is equal to normal stress upon longitudinal stress, and that will be equal to normal stress equal to y Z by R, and Z by R we already derived from here longitudinal stress. So if A be the area of cross section of the filament, then shearing force is given by stress into area, and that will be equal to y Z by R into A. Okay, therefore moment of this force equal to y A R y A by R into Z square. Okay, Now the sum of moment of all these forces of extension or compression given is gives by the internal bending of moment, that is G equals to summation of y r a z square. And when we do mathematical term here, we when we put Ig is equal to summation a z square, and Ig is geometrical moment of inertia, so we'll get the formula G is equal to y by r Ig, which is very important formula. And we can say G is torque here. And now also why Ig is known as flexural rigidity. If A is cross-section area of the beam and K is radius of gyration of the cross-section about the axis passing through the centroid and perpendicular to the plane of bending, then Ig is equal to AK square. So internal bending of moment, G is equal to Y by R Ig, or G is equal to Y by R AK square. Okay, you can see the case for rectangular beam and for circular beam. Okay, thank you. This much for today.